started.
All right, so thanks to everyone who's back for the last part. As always, I'll start with, first, my goal for today is to talk more about ether and the stabilizer group. We'll see later what those things are. But as always, let's start with a quick review of what happened last time. So last time, we began by talking a little bit about the chromatic convergence theorem, which said that the P localization of X is the homotopy limit of these Ln localization, which were the localization at the first, or I guess.
Excuse me, Agnes? I'm having a lot of trouble hearing you. I think there's a volume issue.
Is anyone else having trouble hearing me?
It is a little quiet, but if I just turn my volume up, then it's working.
Let's see. I don't know how to fix this.
Yeah, maybe just if you can speak closer to the mic, that might just be enough of a solution.
Okay, let me try to speak at least louder. Is that better?
A little bit.
Okay. I can start digging for where my mic is, but I don't know.
All right, I would just keep going.
Okay. And I mentioned that this is the same as the localization at the Johnson-Wilson theory, and also if you just take MUP and you invert Vn. So this convergence theorem led us to define the algebraic chromatic filtration, which was, obtained by taking the kernel of the maps on homotopy groups induced by the localization from X to Ln minus 1. Then we discussed type N spectra. So at first I defined these to be finite spectrum X, whose Kn star homology is non-zero, and such that Kn minus 1 star of X does vanish. So I talked about theorems such as the fixed subcategory theorem, but one of the theorems that we discussed was that type N spectra have Vn self-maps. Okay, so they have self-maps that have nice properties with what they do on Kn star homology. And these Vn self-maps, we saw that they gave rise to certain periodic families in homotopy groups, and I showed some pretty pictures. And then, so towards the end, I talked about how if you have a type N spectrum, so for certain type N spectra with a Vn self-map, I had defined tel n to be the telescope of X with respect to that self-map. I made a choice, but it really didn't matter which choice I had made. Okay, and then we defined the telescopic localization of X. Sometimes people call it the finite localization, to be the localization with respect to the wedge of these telescopes. And that led us to define another filtration, which I called the geometric chromatic filtration. And that was obtained by taking the kernels on homotopy groups for these localization maps. And then the last thing we talked about was the telescope conjecture, and that's a conjecture that proposes an equivalence between these two localization, and in particular lead to the fact that the two filtrations should agree. Okay, so again, this is a conjecture, not known, probably believed to be false by most. Okay. All right, so today, what I'm going to talk about is these topics. So I'll give you a second to just glance at it. Now, if you're not comfortable with spectral sequences, don't worry. I'm not going to talk too much about them. I'll give you a way to think about them that will be good enough for today. Okay. Okay, so first let me launch into saying, okay, why care about the telescope conjecture? The telescope conjecture predicts an equivalence between these two functors. The left one has an intuitive description in terms of inverting Vn self-maps. So it sort of captures these periodicity phenomena that were sort of first came up in Adam's study of the image of J. So it's sort of doing the thing we were interested in encoding. However, Ln has chromatic convergence. Okay, and we're going to see Ln is more computable than LNF. So I'm going to talk today a lot about how do we get at things that are Ln local. So this is one of the great appeals of the conjecture. It takes something that we really care about and turns it into something that we can compute, and that captures the stuff we want to know about. Okay. So for today, I'm going to focus on the functor ln, and a little bit later, lkn. Okay, so first let's look at the chromatic fracture square again. So for any x, I mentioned that there's a homotopy pullback, like so. This is called the chromatic fracture square. And so roughly ln is obtained by gluing lkn and ln minus 1, so these pieces, along the intersection ln minus 1 of lkn of x. Okay, so that's that corner. So you want to think about this corner here, ln minus 1 of lkn of x, together with these maps as forming the gluing data for the fracture square. So in particular, it's sort of like okay, I'll say this thing before I say that. So, and this LKN here is like the building blocks that allow you to go from chromatic level n-1 to chromatic level n. Okay, so if you can get your hands on the building block and you can understand the gluing data, then you can sort of proceed in your inductive approach to understanding the p localization of x. Okay. Now, the chromatic splitting conjecture is a conjecture made by Mike Hopkins, and it's about the gluing data. So today, I will only have the chance to tell you about the weak chromatic splitting conjecture. There's also a strong chromatic splitting conjecture. This is a beautiful conjecture. And a place to sort of dive in to learn more about it, there's a little note by Tobias Bartel. There's a link on my website, so it'll be clear by the title, by the name. It's like Telescoping Chromatic Survey. So that's a place where you can go to go look for other references and learn more about this. Okay, so let's see what the chromatic splitting conjecture has to say about the gluing data. Okay, so here it goes. So it states that for a finite spectrum x, and then we're going to take xp to be the p completion, as before, then this conjecture states that this map here, so I meant to highlight, so this map here, this is the map at the bottom of the fracture square, okay? So this map here is supposed to be the inclusion of a wedge summand. So in particular, this thing is supposed to be a copy of this wedge, I don't know why I wrote P, wedge some spectrum X, which is, I guess here I should, I'll write what, so it's often written FN. FN is like the fiber of this map, okay? So the weak chromatic splitting conjecture is just the splitting here. The description of this, that's the strong chromatic splitting conjecture, okay? So this is a beautiful conjecture. In particular, it sort of tells you about some kind of, like, it tells you that the gluing data is rather simple, okay? There's, whenever the lower left piece, it just includes as a wedge summand into this like piece that's used for gluing, okay? So that's one of the reasons why it's so appealing. It's sort of telling you that if you want to climb up the chromatic tower, really the work is just at every step to understand the new KN local data. You don't really have to work so hard for gluing things together, okay? So now in this little box, I tell you what is known about the CSC. So for n is equal to 1 and p is greater or equal than 2, so if you know enough about the computational techniques, this would be an exercise. It follows from the classical computations about K1 local homotopy theory, so names that come up are Adams, Bousfield, Baird, Ravenel. Okay. Now, if n is equal to 2 and p is greater than 5, this is due to Hopkins, who was sort of studying the calculations of Shimomura Yabe. So they computed pi star of L2 of S at the prime. I'll put the 5 there, just at the prime 5. Okay. Oh, sorry. Bigger than 5. So I'll just write it like this for p bigger than 5. So now we jump from here to here, we jump difficulty level, like, you know, it exponentiates. This is definitely not an exercise. These computations are really hard, so much that, there are pictures out there. So Mark Behrens has pictures of these computations and has a paper about them, but it's even the rehashing of it is still difficult to understand. Okay. Now for n is equal to 2 and p is equal to 3, this is more recent, and it's due to Gerson and Mohold. For n is equal to 2 and p is equal to 2, this is even more recent, and this is due to myself, Gorson, Hen. And for bigger than 2, it's wide open. Okay. So in these exercises, the CSC is proof by brute force computations. We compute the left-hand side, we compute the right-hand side, we check. Okay.
Agnes, this is process. I have a question. Is there any conjecture with ln f which is similar to chromatic splitting conjecture, or people have any expectation one way or the other?
I don't know. I've never heard of it, never thought about it.
Okay.
But cool question. I like the question.
Okay.
Yeah. I mean, somehow when you put it all in one slide, it seems like one should ask that. It just never occurred to me. Okay, so now to prove this more generally, I think we're going to need some more conceptual ideas. Okay, so that's the CSC. I encourage you to read more about it. It's a cool conjecture. And it has cool consequences. So one of them that's easy to state and that's been motivated already. So the CSC would imply that for finite spectra X, we get chromatic convergence for the spectra, for the localization LKN. So the homotopy limit so one of the things you get from the CSC are structure maps to form this homotopy limit. And the CSC would, together with the classical chromatic convergence, would give you chromatic convergence for the P completion. Okay. All right, so now, if we want to sort of say that we're going to study the sphere, climbing up the chromatic tower, then we need to know how would we study these chromatic layers anyways? And maybe more fundamentally, how do we study the sphere? Okay. So for today, I'm going to focus on how do we study the homotopy groups of these things. So before I can answer the first question, I'm going to talk about the second. So one of the key tools, so there are various tools, but one of the key tools is the Adams-Novikov spectral sequence. And let me try to explain to you what this is, or at least motivate it. So remember that mu is a ring spectrum, so it has a unit and it has a multiplication. Yeah. So this map iota right here, this is not a very good approximation of S. Okay. So for example, let's look at the Hurwitz image. So on pi star, what does it do? Well, it factors through the map from pi 0 to mu star, or pi star S to mu star, factors through, well, killing everything interesting in the homotopy groups of spheres, keeping the Z and then including that. Okay. So Hurwitz image, not so good for understanding the sphere. However, you can keep going. So I just looked at this one map, but we have all of this data of the multiplication. And so we can sort of iterate this idea of trying to approximate mu using its unit and form something called an augmented cosimplicial spectrum. Okay. So this one map here, this is you do the unit on one side, and then so this is mu smash S naught, but it's also S naught smash mu. So you just do the unit on one of the factors and the identity on the other one. And then the map going back is multiplication. And then you sort of iterate this process. So this diagram here, I'll just abbreviate as mu bullet. Okay. So the unit map here, so it starts with this, so it's augmented because this is the augmentation here, this map from the sphere. So although this map wasn't such a great approximation, it turns out that this diagram is. In fact, its totalization, so roughly its homotopy limit or something like that, is going to be the sphere. So let me stop and say something. There's always a map from the localization to the totalization. It's not generally true that this is an equivalence or known. When it is, it's often a theorem. Okay, and in this case, for mu, if you look in the original Bell's field paper, you'll find out that this localization here is the same as the sphere spectrum and is homotopy equivalent to the totalization. Okay, so there's a lot going on in the statement that's sort of special to mu or other spectra. Okay, but here it all works out. So it turns out that mu, as long as you're willing to keep going, can be a great approximation for the sphere. It can hit it on the nose. And from this story, this is where, well, I mean, maybe not historically, but one can take this point of view that this is how the Adams-Novikov spectral sequence is born. Okay, so what's the Adams-Novikov spectral sequence? Well, it's sort of a gadget. So you apply sort of pi star to the diagram. And so if you have an augmented cosimplicial gadget, you can get a co-chain complex by you apply pi star, then you take alternating sums of face maps. So these maps here are alternating sums of faces. Okay, so you can find something which people call the Kobar complex, and this X term here is just the cohomology of this Kobar complex here. Okay, so you just think whenever you see this X for today, you just think apply pi star, take alternating phase maps, the effect of alternating sums of face maps, and then take cohomology. Okay, so it's some algebraic gadget that's more or less computable depending on how clever you are, how much computer power you have. You know, it can actually be hard to compute. All right. But it gives you a machine, which is the spectral sequence, which converges to the homotopy groups of spheres. So basically, you think of this as a first approximation. Okay, but then there are some things that might not actually represent homotopy. So there's a process of sort of getting rid, or people say killing, classes that are irrelevant, and these are called differentials. Okay. All right. So for today, you can think of spectral sequences as a machine whose E2 term is algebraic and whose output gives you what you want. All right. So on the next page, I'll show you an example. So I did it for NU, but I could have done it for BP, the Brown-Peterson spectrum. So you switch to BP when you work one prime at a time. So MUP was a big wedge of suspensions of copies of BPs. Okay. So if you just focus on one of them, you can do the same story, and you'll get instead something that approximates the P-local sphere. Okay. And the picture I have here is Doug Ravenel's computation. I've stolen it from the Green Book of the homotopy groups of spheres of the Adams-Novikov spectral sequence for the prime 5. Okay, so this is prime 5. Okay. And now, okay, so this here, that corresponds to this. So we saw this picture before here. This was Hatcher. I showed it last time when I talked about periodicity. And similarly, this here is this, and so on. Okay. Okay, so I think there's been recent breakthroughs in computing these each page of Adams spectral sequence. So this is, so I encourage you to check out the work of Isaacson, Wang, and Xu. So on this subject, okay? Okay, so that's if you're just like going at it directly. Okay. However, okay, so let's remind ourselves of something called the Mohold uncertainty principle. So it says that if you have a spectral sequence and it converges to the homotopy groups of spheres, I guess there should be an S here, and suppose that the ether term can be named using homological algebra. Okay, so you remember that X over mu star mu, that was homological algebra. It's just algebra, right? So if you're in this situation, then there will be so this E2 term, it will be infinitely far away from the actual answer. So that means that the differentials, these things that were killing things that shouldn't be there. So I like to think of it as they create carnage. Okay, so there's just so many of them, and that's that. Okay, but that that hasn't stopped people. So the world expert is in the room. It's Dan. Okay, so that doesn't have to stop you. But for a while, it might divert your attention. Maybe you're like, okay, I won't go at it directly. Instead, I'm going to try to climb the chromatic ladder, okay? And I'm going to try to study this or this instead. And that has been a popular approach in this problem, okay? So that's going to be the goal for the rest of the talk about that. Okay, so you can do the same story using other homology theories. So right now I'm going to look at the case of EN, the Johnson-Wilson spectrum. Okay, so I guess if you don't remember, EN star was ZP adjoint V1, Vn minus 1, Vn plus or minus 1. Okay. So recall that its localization functor is the localization functor ln that we've been interested in, okay? And if you look at this first approximation here, well, it has to factor, because this is En local, it has to factor through the localization, okay? So maybe the best you can hope, in the case of mu, this was true, but the localization was the same as the sphere. However, if you don't happen to have this localization be the same as the sphere, which it's not for En, the best you can hope is that the machine you come up with will sort of tell you something about this spectrum. Okay. And now it's a theorem. So I tried to figure out who this was due. I think it's Ravenel. I'm going to say Hopkins Ravenel. So I didn't write it in because I wasn't sure. But sort of the theorem would be a sort of the content of this thing. So afterwards, feel free to email me and tell me who I should have credited here. But it's, if you want to sort of learn more about it, it's proposition 6.5 in Hovey-Strickland. The paper, there's only one link to Hovey-Strickland on my website, so that's the one. Okay, so it says that, again, if you take this cosimplicial gadget and then you take its totalization, what you recover is ln of s. So that maybe you don't start as a good approximation, but if you don't stop, then you'll get what you wanted. And from this sort of story, you get the En-based Adams-Novikov spectral sequence, and the E2 term is similarly defined, but this time it converges the homotopy groups of ln of s. And part of this story, so this is a little bit, this all goes together, but part of the story and the proof of these facts is that this En-based Adams-Novikov spectral sequence has a horizontal vanishing line at some error page. So what this means is that this machine here, it stops. Okay, so you sort of start computing the stuff, and in some finite amount of time, then in theory, you should be able to start here and end with the homotopy groups of this thing. So this is very different from, say, mu and the Adams-Novikov spectral sequence, the classical one, which would have like lots of differential, and the difference is that this won't compute the sphere this won't compute the homotopy groups of spheres, but some other approximation of it, as in the nth chromatic layer. Okay. Now, so that's for ln, and now what about for Lkn of s? Okay. So for Lkn of s, I need to introduce a new theory, and this is Morava E theory. It hasn't come up yet, but the tools to build it have all been introduced. So we're going to fix a prime p, and I'm going to use the notation zp to the n to denote you take the p-adic integers and you adjoint a primitive p to the nth minus 1 root of unity. Okay, and the notation is motivated by the fact that if you take zp to the n mod p, you get fp to the n, the field with p to the n elements. Okay. Now, E star, so we're going to start by defining the coefficients, and then we're going to use Landweber exactness, okay? So En star, the coefficients is going to be Zp to the n, adjoint a power series on n minus 1 variables, and then a periodicity element. These formal variables, they're in E0, okay? So they're all in degree 0. And U, the periodicity, I'm going to place in degree 2, okay? Watch what you read. Sometimes we put it in -2. It just depends how the person is feeling. Okay. All right. So now Morava E theory, En. is going to be the Landweber exact theory, which is associated to the following map from mu star. So you first go to En star, okay, and then you do the map from this ring, which is En star, to this new ring that we just defined, and you send Vi to the following list, okay? So I guess there's none of these, so I didn't need that, okay. Okay, so remember that means that the theory is going to be defined by this formula. Okay. All right, so the spectrum is called Morava E theory. Sometimes it's also called the Lubin-Tate spectrum. Depends who's talking. Okay. And for n is equal to 1, you can check, you just get the P-complete K theory. Okay. Now, okay, so what are some facts about this functor? So we don't get a new localization. Ln is, again, Len. So now we've got a lot of ways to talk about this localization functor. Okay. This En is like a periodic version of Lkn of En. So remember I said that Lkn was supposed to be like completion at V1 up to Vn minus 1. Okay. So now this is, so these variables, the UIs, they're just some, there's just some shift of the VIs. Okay. So, and you can see that in En star, you've got these completions here. This is, you've completed with respect to that. Okay. So that's why I say that En is a periodic version of Lkn of En. And as such, it's Kn local. Okay. So that means that Lkn of En is En. However, that doesn't mean that En smash En is Kn local. Kn localization does not play well with smash products, except in special cases. So what we're going to do is we're going to declare En star En to be not what you'd think. So usually what En star En would be is we would take that out and it just would be pi star of En smash En, but we're not going to do that. We're going to take pi star of Lkn of En smash En. So this thing here is supposed to be internal to the Kn local category. So you want to sort of, whenever you're working Kn locally, if you smash, you want to relocalize because you might have gotten out of your category if you don't do that. Okay. So sometimes, in the literature, sometimes people will put a V there to denote this thing. Okay. So I want to, yeah, that's what I wanted to say. So why are we doing this? I mean, because of this, if I just ran the other story that I did, like where I took like, I looked at S0 going into En and then I like did some stuff, then maybe like I would just recover the other story, the one that I got for En. And I don't want to recover that story. I want to recover a story that's going to give me Lkn of X, of S0. Okay, so that's why I'm going to work to stay in the Kn local category. All right, so now we're ready for the Kn local En base Adams-Novikov spectral sequence. So En is Kn local. So if I look at this first approximation here, it has to factor through the Kn local sphere. Okay, and this is a theorem. So I'm going to say Devenotz-Hopkins on this one. Okay. And the theorem is that now if you do that, if you do this approximation and you take this like big complex, but every time, so in this diagram, we had like En goes and we had these two maps going back. So instead here of putting just En smash En, I put the Kn localization and I don't know, and so on, Lkn of. Okay. So I localize every time, I just stay in the Kn local category. And if I look at the totalization of this thing, I do get the Kn local sphere. So from this, we get the thing that people call the Kn local En base Adams-Novikov spectral sequence. And this X here, you can identifying with an X in some category, but for now, I just mean like the cohomology of this Kohlberg complex that I mentioned before. And it converges to the homogeneous groups of the Kn local sphere. And part of this story and part of proving this is that this spectral sequence also has some vanishing line at some ER page. So that's the machine that we use to compute for the Cannes local sphere. Okay, but now it's nice, we have all these machines, but like, so this EN, this new thing, where does it fit in our formal group law story? Okay, so MU, that was sort of, it classified all the formal group laws. EN, so the Johnson-Wilson spectrum was related to the formal group laws that had height less than or equal to N. So where does this one fit? And for that, I'm gonna review a little bit this formal group law stuff. Okay. So first, okay, so this happened at the end of talk 2, but I did it really fast, so I'm gonna do it again. So what are strict isomorphisms? A strict isomorphism of formal group laws is gonna be a homomorphism. Okay, so it goes from this to that. So remember we had this notation, which was convenient, and in terms of power series, is really just means this. Okay. And it's going to be a strict isomorphism if the leading term of F is just X. Okay? So this forces F to be an isomorphism, but it's more than an isomorphism. We want the first coefficient to be 1. Okay? And then I'm going to call the other coefficients Ri. So now, okay, so we have formal group laws over R, and we have a class of morphisms which contain the identity, so we can form the groupoid, which is going to be the formal group laws with strict isomorphisms. So we formed a category, but it's a groupoid because these are isomorphisms. And this actually gives us a functor which goes from graded rings to groupoids. Okay, so it takes R and then spits out this groupoid here. Now, remember, a morphism in this groupoid is going to be a triple, so it's going to be 2 formal group laws and a strict isomorphism between them. Okay. Now, okay, so maybe one of the key remarks is that if F is a formal group law and F of X is as above is our strict isomorphism, then G is completely determined. So it's this formula here. Okay, I just rewrote it differently. So it's completely determined by F and the little f. Okay. So morphisms in this category here is determined by the formal group law and the strict isomorphism. So we only really need that data. G just comes along for the ride. All right. So now, so this is part of Quillen's theorem. Mu star mu, well, that's by definition this thing. So this happens to be the thing that classifies strict isomorphism between formal group law. So you get a polynomial ring on mu star as the coefficients and on classes B1, B2, and so on. And these B1, they're supposed to be these Ri's here. So if you have a map from mu star mu to a ring, R star, well, the effect on the map on mu star here gives you the formal group law. Remember, so if you restrict phi here to R star, then that gives you the formal group law. And the Ri's are the image of these BI's. So the coefficients of the strict isomorphisms are just the image of these guys. Okay. So that's what mu star mu classifies. And then so we have that mu star and then this pair mu star with mu star mu, it represents graded ring, a functor from graded rings to groupoids, which takes R to formal group laws with strict isomorphisms. Now, you can sort of think about a similar story for En star, and what it's going to represent is going to take, well, it's going to take graded p-local rings to groupoids, but the groupoid it's going to spit out is the formal group laws that have height less than or equal to n. So this is the height together with their strict isomorphism. I say roughly because this should really say p typical, but I don't want to explain that. Okay. So if you replace En by Vn minus 1 MUP, then you get exactly what I would. Okay. All right, so what about En star? What about Morava E theory? Well, okay, so it turns out this is related to another functor from rings to groupoids. And I wrote def here, and I'll explain more. It's related to a functor which takes a complete local ring and then associates to it certain deformations. of a formal group law. Okay, so it's got a bit of a different flavor, but it fits into the same general philosophy. So let's see what that is. Okay, so now before I jump into who En is, I need to tell you, I need to get rid of gradings. So I'm gonna get rid of gradings, okay? So that's just because this next story works better. Remember, En is periodic. It's got this U. You can move everything from any degree to back to degree 0 using U. So we're just gonna sort of focus on the degree 0 part. Okay, so we've got a map from Kn star to Kn 0. You just take V here and you make it equal to 1, Vn. Okay? So the image of the formal group law for Kn over this gives you a formal group law gamma n, which has height equals n, and it's defined over Fp. And similarly, you can take En star, you can set U equal 1, and then you get a map from En star to E0, it maps U to 1, and then you can look at the image of the formal group law for En, and that gives you a formal group law over this ring here, E0. Okay. So we're just going to work over E0 and K0. Okay, so what are these deformations? So okay, so in this slide, B is going to be a complete local ring. It's going to have a maximal ideal, which I'm going to call M. I guess I should have called it MB, but let's ignore that. And so Q is going to be the map, the quotient map from B to B modulo its maximal ideal. Remember, this is a field, okay? And okay, so what's going to be this deformation functor that En is supposed to be related to? So a deformation of gamma n over B is going to be a pair, okay? So it's going to be a pair of some I and some G. So G is a formal group law over B, and I is some inclusion of Fpn into this quotient, B mod MM. So this is a field homomorphism, okay? And what's the condition? So we want that if we apply Q to the coefficients of G, so we take G and we do G mod n, then we get what we get from taking gamma n and putting it as a formal group law over B mod n. Okay, so in other words, I star, remember that's applied to coefficients, Q star applied to coefficients, so these two meet over here. All right, so it's like the easiest way that you could talk about over a general B, ring B, how could you say that a formal group law G, if you look at it modulo the maximal ideal, you get gamma n, okay? You need this extra sort of identification of Fpn into that before you can say that, okay? Okay, so the kind of isomorphisms that we're going to be interested in for this groupoid are going to be called star isomorphisms, okay? So a star isomorphism from one deformation to another, oh, I switched my pairs, that's okay. So this is an isomorphism of formal group laws from G to G prime, but there's going to be one condition. We're not going to look at all isomorphisms. We're going to ask that Q star F is the identity. So let's look at this. So we have this isomorphism on top. I drew it like that. My squiggly arrows I'm following Charles Resk's notation. And so one place to look for this is notes on the Hopkins-Miller theorem. So this is notes by Resk. So I'm following his. Okay. Okay, so we've got this map here. Okay. And we want that, okay, if I mod up by Q star, I get this, that's being a deformation. Mod up by Q star, I get this, that's being a deformation. But now you get an induced map after you mod out, and you want that to be the identity, okay? So equal here means identity. Okay? So it looks, once you mod out by the maximal ideal, it's the do nothing map. All right, so we can form the groupoid. Def gamma n Bn is gonna be the groupoid that has objects, the deformations, and over B, and morphisms, the star isomorphisms. So maybe let's make a note. I didn't give you any homomorphisms. Here I had I and I, they matched. They didn't need to match. There might be multiple maps like so, okay? But in this groupoid, we don't allow maps. So for there to be a map, you have to have an identification of this inclusion here, okay? So like, you know, just almost by definition, this thing splits as a disjoint union over all of the embeddings of Fpn into B mod M of these deformation deformations, where here I've put the I here to mean that these are the pairs G comma I. Okay, so where you fix this embedding. All right, so that's the deformations. Okay, so roughly, how do you think of them? So you've got some ring, and you've got your formal group law of height n, and you want a formal group law over the bigger ring, so that when you mod out by the maximal ideal, you get gamma n. Okay, so that's all, like that's the essence of the slide. Okay, so it's a lift. Okay, so, but there's this wonderful theorem of Lubin Tate, which classifies these deformations, okay? So I didn't say that, so provided that there is, so before you can get deformations, you need an embedding of fp to the n into, so you need a map from fp to the n into b mod m, okay? So provided that you've got the residue field of b is an fp, so is an extension of fp to the n, then you'll get that this is, then that this is not empty. Oh, the way I phrased that is not good. Okay, so I don't want that. Okay, so we're gonna assume we have some embedding here. Okay, then in that case, these deformation are going to be in bijections with. Okay, so so I need to rephrase this. Okay, so if you look at this deformation, this groupoid, okay, you can look at pi naught and pi 1. And what the Lubin-Tate theorem says is that pi naught is going to be in bijection with, you take the maximal ideal, now this is the maximal ideal of B, okay, times with itself n minus 1 times, okay? So what does it mean? So a deformation, picking a deformation up to star isomorphism is the same as picking n minus 1 elements of the maximal ideal, okay? And how do you think about this? These are going to be the choices of the coefficients of xp to the k for k is equal to 1 to n minus 1. Okay? So remember, that's related to the Vn. So you pick the coefficients of xp to the k of these powers. And then now it turns out that if you mod out by those, you'll get, if you mod out by m, having picked those, the thing you're going to get is going to have height exactly n. Now, the second part of the Lubin-Tate theorem is that pi 1 of this thing is just 1, okay? So in other words, if you have 2 of these deformations, there's a unique star isomorphism between them, okay? So it's a very well, like these deformations over complete local rings, they're very well understood, okay? Okay, so then that's the first part of the Lubin-Tate theorem, but there's a second part, there's a representability part, okay? So, and the second part is that this formal group law, Fn, that we define, which has coefficients over this ring here, En0, and this is its maximal ideal, then this pair of this ring and this formal group law represents the deformations of the star isomorphisms, okay? So what does that mean? So it means that pi naught of this thing is isomorphic to the homomorphisms from E0. So this is En0. From En0 to B, okay? So homomorphism from this ring to B. There's a topology here. These are complete local rings, so C here just means continuous, okay? So how does that go? If I have one of these homomorphisms, then I just apply phi star to the coefficients of Fn. And what I get is I'll get a formal group law, which will be a deformation. It might not be G, but it will be star isomorphic to G. Okay, so that's the fact that it's representing pi naught. Okay, so in diagrams, so I've got my morphism, my homomorphisms of ring, okay? And so now I've got my universal deformation, which sits over gamma n. And so this phi, if I apply it to coefficients, I get a diagram like this. So I get this phi star of n. It might not be G, but there's going to be a star isomorphism between phi star of Fn and G. And that thing has to be unique just because of this thing. Okay. Okay, so maybe it's a bit to sort of take in at once, but the idea is that, so roughly, so you've got deformations, they're lifts, and they're classified by homomorphisms from this ring into B, and the universal example is the formal group law of En. Okay. All right. Okay, so now what's the stabilizer group? So the stabilizer group is like, so okay, so you've got something that sort of, so you've got gamma n, and you've got like the deformations of it, and you've got something that represents these deformations. Okay, but this thing has a group of automorphisms. So there's automorphism that act on this, and just because of the representation, the fact that something represented, this automorphism group will act on the representing object. Okay, so let's see how that goes. Okay, so Gn here, so it's an extension of the automorphisms of gamma n, so I mean isomorphisms of formal group laws. Okay, but it's a bit beefier. It's the pairs. So F is going to be an isomorphism between, so I is going to be an element of the Galois group, so it's a field automorphism of Fp to the n, and F is an isomorphism between what happens if you apply I star to gamma n onto gamma n. Okay. So now the product is given by, well, it's what you have to do, right? You just look at this composite. Okay. So there's a bit of a twisting, and in fact, Gn is isomorphic to the semi-direct product of this Galois group here with this automorphism group. Okay. In the literature, this guy people call Sn often, especially recently. All right, so Gn acts on E0 as follows. Okay, so if you have one of these pairs, then you can pick any g of x in E0 in the power series ring on E0, which reduces to f of x mod m. So remember, f of x is in Fp to the n of x. Okay. Okay. So you pick a lift, okay? So it might not be the right lift, it might not be, so it's just some lift, okay? But now if you look at this pair here, so if you let G be this thing, okay, so you have your lift G and you just conjugate Fn by this G, then this G of x is going to be a point in the deformations of gamma n over En0. Okay, so this thing is a deformation. So if it's a deformation, that means that it's classified by a homomorphism. Okay, so in other words, so here, this diagram here, that's this diagram here. Okay, so I've got phi star applied to Fn. This might not be Gn, but it's star isomorphic to Gn. It might not be G, but it's star isomorphic to G. Okay. And then I've got, so just the way this is defined because of this G in front and the G inside, like the power series G is a homomorphism going this way. Okay. So now this gives you an assignment. So alpha goes to phi alpha, okay, which is a homomorphism. So it's written right above, I won't repeat it. Okay. And so now you're like, okay, but you made a choice, right? I picked this G of x, okay? I've picked a lift. But you can check that even if you change the lift, this assignment alpha goes to phi alpha together with this composite here, those won't change, okay? So actually, even though you made a choice, the whole total thing doesn't change. And it's because of this uniqueness of star isomorphisms. That's why it's choice independent, okay? And the way that Gn acts on En star, it acts via phi alpha. So alpha goes to phi alpha, and that's the action of Gn on En star, okay? So that's the hands-on way to understand how Gn acts on En0. Now, we don't just have En0, I've been seeing En star, but I'm at En0. we actually have a whole, En had like periodic thing, okay? And the way that we extend the action is you take this class U, which we forgot when we told the Lubin Tate story, and you put phi of alpha U is this number times U. So this is, so phi alpha, this is the first derivative. So it's going to start with phi alpha of, so it's going to start with some coefficient B, X plus higher order term, and this whole thing here is B minus 1. Okay. All right, so you extend it to En star, okay? Now, okay, so maybe what to remember, En classifies deformations, Gn, the group of like the automorphism of the thing you're deforming, act on En. So now you've got this big group acting on this thing, and actually it sounds completely mysterious at first, but the example for n is equal to 1 is something that is super classical. For if n is equal to 1, what you recover is going to be the action of the atom's operations. Okay, so if n is equal to 1, E1 is P-complete K-theory, E1 star is this ring. The action on E1 0 will be actually trivial, and all you'll be left with is the action on the Bach class. Okay, and G1 here is ZP cross, and it acts on C star by the action of the atom's operation. So opposite here, it's this inverse here. So it kind of gets the opt action. Okay. So how do you want to think about the group Gn? It's the higher atom's operation. Okay. So so E1 is P-complete K-theory, and En is supposed to be like this, its generalization. P-complete K-theory has atom's operation. Gn, that's the analog at higher heights. Okay. So now a hard theorem is that, okay, so we have this action of Gn on En star, right? We have Gn acting on the homotopy groups. Okay. Well, so something difficult to prove is that actually this group Gn, you can think of it as acting on the spectrum. Okay, so it doesn't just act on the spectrum up to homotopy, so it doesn't just act in the stable homotopy category, it acts in spectra, so now in the category spectra. So the words for this is that it acts by maps of E-infinity ring spectra, okay? So if you know what that is, that's great. If you don't, think it's the best kind of actions you could get, okay? So it like acts honestly, just like on the nose, and it respects all kinds of great things, okay? So you want to think of En as a ring, so as a commutative ring in the most rigid sense that you could think of, and the group Gn acts on this commutative ring by maps of rings, the best kinds of maps of rings that you could hope for. Okay. So what's the point here? So the point of this here is that we're going to take all this algebra that happened in the Lubin Tate story, and then we can transfer it to spectra. Okay. So now, just a quick reminder, so maybe this is a breather from the previous couple slides, which going through them now, I realize we're quite technical. So group cohomology, okay, if you have a discrete group, how do you compute group cohomology? Well, one way that you can do it, if you look at Wikipedia, that's what it'll tell you to do, is you can form the Kolbar complex, okay? So this is formed from the co-simplicial abelian group, which is, which looks like something like that, okay? And then you let delta act by alternating sums of face maps, and then you take the cohomology, and then you get group cohomology, okay? So it feels a little bit like what I was talking about for the eXT groups that I mentioned earlier, okay? So that's like refresher 1, refresher or new definition 2. So what's a Galois extension? So you know what Galois extensions are in algebra, like with fields and stuff, but these definitions have been generalized, so you can talk about Galois extension of rings. So now I'm talking about honest rings. What's that going to be? It's going to be a ring homomorphism from S to R, such that, so R is going to have a G action, okay? So R has an action of G, and that's by ring homomorphism. So just like in the sort of extensions of field case, you have where the Galois group act by field automorphisms, okay? And we want that S is the fixed point for the action, okay? And furthermore, you need to ask, if you want to recover the theory, you need to ask that if you take R and you tensor over it over S with itself, you get hum from G to R. Okay? So that's like, oh, I'm forgetting the word. It's like, I want to say normal basis type of stuff. Okay, so now let's see, I'm going to have these sort of, in the next slide, you're going to see things that are going to remind you of what you're seeing on this slide. Okay. All right, so first, co-operations on E-theory. So, you know, you have cohomology operations, if you remember your topology class. So like say the Steenrod algebra is A, so that's the cohomology operations. And then if you do HFP, that's like the dual of the Steenrod algebra, that's what people call the co-operation, okay? So we've seen some MU star MU, those were MU co-operations, okay? Well, in fact, there are isomorphism. En star is going to be isomorphic to, well, so En star is by definition this thing, and it turns out that it's isomorphic to, you take, so what is this? So think of this as functions from Gn to En star. The C means continuous. These things have topologies. You have to take them into account, okay? So it's going to be functions from Gn to En star, okay? And okay, so what's sort of a reason you should think maybe something like this would happen? Well, remember, MU star MU, that was like strict isos, right? It was a point in MU star MU was a formal group law with a strict isomorphism to another formal group law, okay? This Gn here is like the automorphism of the gamma n, okay? So, and that's the, so proving something like this comes from sort of going down that road, saying like, okay, I've got this interpretation of MU star MU as strict isos, what does it give for En star? Okay, and it leads to the fact that you should see that En star sort of should encode some data about the isomorphism of the thing that it's deforming. Okay, this, you know, this theorem. So you read the literature. So there's a paper of Hovey, which is like E star operation and core operation. It's on my webpage, and he sort of tries to give credit for this. So the names of like Mike Hopkins come up, Morava come up. Ravenel come up, but the first published proof, he says, is by Andy Baker, okay? So go in there if you want the proof, and so there's a proof in there too, and more information on it. Okay, but now, so this part here, this is the sort of, I should have put it in the thing, so this is the work of Deformations Hopkins, okay? So this is one of the seminal paper. It's not on my webpage, I will add it. And it just like sort of lifts all of the story to spectra, okay? So, so we had this En star En was this. So from that you take, you know, this co-simplicial gadget, En goes to En smash En and so on. And then you can localize this. That was this guy. Well, this thing is going to look like this co-simplicial gadget, which here, this should remind you of the Kohlberg complex for cohomology. Okay. And okay, so we had the LKN is the totalization of this. Deformations Hopkins proved that it's also that these two totalizations are equal, and the totalization of this thing, that's what they define to be the homotopy fixed points of En in terms of Gn. Okay. Okay. So and this is not arbitrary. Okay. So now, if you look at it in this context, then the En base can local Adams-Novikov spectral sequence. So the spectral sequence you got from this, that it'll be the spectral sequence you get from this one here, but the spectral sequence you get from something like this, that's going to be a homotopy fixed point spectral sequence. Okay, so in recent years, the things that people use, one of the things that people use to study the homotopy groups of the K local sphere is this spectral sequence, this homotopy fixed point spectral sequence. Okay. And now if you put all these things together, you should, so F here is like functions, okay? So you've got like En star En is like the functions from Gn to En star. You have that LKN is the homotopy fixed points. And together, like in the, so if you put this in the language of Galois extensions of ring spectra, which was sort of introduced by Rognes, it says that the map from LCAN of S to, oops, I should have, this map here is a GN-Galois extension of ring spectra. Okay. I'm going to skip this because I don't think I have time. I'll just say quickly, so we've got this moduli stack picture. We had like all these open sets. And the role of En and Gn is the En with its action of Gn picks up this formal neighborhood around the point of height exactly n. But on this note, I'm already late, so I'll say thank you. I want to say thank you. I also want to say that there are a lot of people that did a lot of work that went towards the things I was presenting today. And I gave credit to the obvious people like Doug Ravenel, Mike Hopkins, Ethan Devenatz, Haynes Miller came up. But there's a lot of people like Steve Wilson, Mitchell, like a lot of other names. I'm going to stop there because I tried to make a list and I was afraid I missed somebody. So there's a lot of people out there that have made great contributions to this field that I haven't mentioned, and I want to thank them. And this is a picture of a conference. I think it's the Peter May Birthday Conference that happened in Boulder, and there's a lot of faces I would like to thank in there, so I decided that I would use this picture as my last slide. Thank you.
Okay, I'm going to unmute everyone so we can thank her. Okay, and I'm going to mute everyone again to cut down on the background noise. Okay, and are there any questions? All right, well, if not, then we will wrap the series up here. Thanks everyone again for participating. My feeling was that this was a great success, that this was especially useful to graduate students at the right level. And I am hoping that we will do something again similar in the fall with details to be announced, okay? All right, thanks again, everyone.